Welcome to SanfordFlipMath. This is PreCalculus. We are working through the Demana, Waits, Foley, Kennedy book, 4th or 5th edition, depending on which book you have, because we have a couple different editions floating around here. We are just about wrapping up the trig graphing section, chapter 4. And today is about, this video is about inverse trig functions. I know that looks kind of weird seeing the y equals x squared up there because I need to establish some background. And really, the big issue here is about the domain and range of what are normally accepted as the inverse trig functions. The problem, we're going to go on a little excursion here. The problem with trig functions is, as you know, if I just graph y equals sine of x, and I'm going to be in radians here, and I'm going to do this on just a standard screen so that we get a certain look when we're done. Okay, so there's sine. The problem is that when I actually graph the inverse of this, and if I type in, see, this, what I'm about to do isn't really going to work, and I'll show you why. I mean, it works, but you'll just see. Okay, so here's the inverse sine function. Well, I don't know if you saw it come up there, but it's there. Let me do, oh, that's even bold. That's great. I'm going to clear it. Okay, so here it is without that inverse sine function right there. Okay, and then let me put it back in. Okay, so second sine, and the problem, you know, it just does a little chunky thing, and it's there, but you can't hardly see it. So let me do this instead, and this is kind of convoluted, but it works, and that's what I like about it. I'm going to go to the Draw menu, which is here above the Program key, and I'm going to pick the one that says Draw Inverse, and that's actually, I believe, number 8. Oh, a little bit too far. There it is. Okay, so Draw Inverse, and I'm going to draw the inverse of sine. Now, what this is going to draw is the actual inverse of sine. I know that's clever, isn't it? And what I mean by that is it's going to switch all of the x and y values of the sine graph. So here's y equals sine x, and now here comes the invert. Wow, look at that thing. Now if you think about it, all of the x and y values have to switch. So this entire cycle has a bunch of x values, well, and y values. Well, here are those same x and y values, only they traded those values. Now this is not a function. In other words, this doesn't pass the vertical line test. In yet another set of words, if I pick an x value for the inverse, like say 1/2, well, here's pi over 3 or pi over 6. Here's 5 pi over 6. Here's 13 pi over 6. Here's more than that. So the problem is that for that one x value for the inverse, 1/2, there are many, many, many y values for the inverse, angles, that make that true, and that's a little overwhelming. Okay, so what happens is we actually limit things, and let me clear the ink off of there, and let me get rid of this. And so what I'd like to do is take you back in time for just a little bit. I'm just going to clear that drawing off of there. I'm going to take you back in time for just a little bit to y equals x squared. Okay, and we're not going to spend a lot of time here because this is really not what it's about, but the concept is there. If I take these ordered pairs, let's say I have 0, 0, 1, 1, 2, 4, this is y equals x squared. If I want to do the inverse of this, so let me do -1, 1, and -2, 4 also. If I want to do the inverse of this, okay, so x and y inverse, and I don't mean the reciprocal here. All I'm going to do is switch the x and y values. Okay, so here's 0, 0, 1, 1, 4, 2, 1, -1, and 4, -2, and there it is. Now, this, like sine and its, quote, inverse, it's not a function either. In other words, this x value 4 has two different y values, not a function. It does not pass the vertical line test. If I pass a vertical line through, it catches in more than one spot. So if you recall, what we normally think of as the inverse of y equals x squared, what we normally think of as the inverse of squaring is square rooting. Well, if I graph y equals the square root of x, it's not all of that. The square root of x is just this much. It's only the positive part. We oftentimes stick a negative in front of it to get the other half, but it's really only the positive part right now. Okay, so what we need to do then is apply what we just did to trig functions as well. Okay, so for instance, let me just take a peek over here. Nope, not too early for that. So what's going to happen is we know sine looks like this, and this is just a very rough sketch. And when I do that reflection over the line y equals x that happens when we do inverse, it looks like this. Looks like some crazy snake climbing the y-axis. But to make this into a function, what we're going to end up doing is clipping off a bunch of stuff. And I need you to understand what we're taking off and why we're taking it off. So, and the whole point of it, okay, and this is a big deal, the whole point of it is to make it a function. Okay, so, and that's what is going to happen. Okay, so here's the process. So the problem is the inverse of a trig function is not a function. The fix, what we're going to do is force it to be a function by clipping off stuff from the range of the inverse, or in other words, from the domain of the original, so that the inverse will be a function. Okay, and then that's the biggest issue, is it needs to be a function. We also need to include quadrant 1 in what we're doing. In other words, sorry, I forgot to change that to 2 pi. We have to include 0 to 90 degrees because those are very, very common angles, otherwise known as, that's supposed to be pi over 2, sorry. In other words, we have to include, that is just annoying me now, sorry, pi over 2. So from 0 to pi over 2, sometimes it's going to include the 0 in the pi over 2, sometimes it's not. And then the range has to include all of the range of the original. In other words, if sine originally goes from negative 1 to 1, then we have to include it. If tangent originally includes everything from, for all real numbers, then we have to include it. And we would like it to be continuous. Okay, so what's all that mean? Okay, again, what we're saying is the original sine graph looks like this. Okay, so here's 0, pi, 2 pi. This goes from negative 1 to 1. Okay, when we do the inverse of this thing, here's pi, 2 pi, negative pi, negative 2 pi. We're switching x and y values. This is 1. This is negative 1. Sine starts at 0, 0. It ends up at 1 for pi over 2, and then back to 0 for pi. And I know this feels really weird graphing it like this. And we're not going to do a lot of graphing like this. It's just enough to get an idea of what's going on. Excuse me. And I know I'm not working on a grid here. I just am kind of freestyling it. Okay? All right, so let's look at our criteria. We need to make this a function. Okay, so as we cut things off of this, we will make this a function. And again, the test for a function is, does it pass the vertical line test? Okay, so here's a vertical line, random vertical line, whatever. And this obviously does not pass the vertical line test. It hits in a whole bunch of spots. Same here, same here. All right, save that for later. Okay, so we need at least from 0 to pi over 2. Well, here's pi over 2. Okay, so anything that makes this so it's not a function outside of that is gone. Like, for instance, that little chunk. Okay, so now at least the right side of the graph is a function. this little guy right here now passes the vertical line test on that side of the graph. It doesn't pass it on the left side yet, but it does pass it on the right. Okay. We want to have all of the range, so we need the left side in this, all of the range of the original, in other words, all of the domains. So if the range of the original went from -1 to 1, then this graph has to cover from -1 to 1. I need something to deal with, whoop, oh, that was not good at all. Can I undo that? Yes, thank you. Whew. All right, so let's point with the mouse. I need something that takes care of this part also, the left side of this graph. Okay, but I also need it to be a function, and I want it to be continuous. Well, this little piece right here would cover my left part of this graph, and it would make it continuous. So what I'm going to do is get rid of that little piece, and let's get rid of that. So all I'm left with is this little nubbin of a piece of graph, and where this goes is from -π/2 up to +π/2, and for domain it goes from -1 to 1. Okay, so this is a graph for what is accepted as inverse sine. And if you notice, every time you take an inverse sine in your calculator, it only gives you values between -90 and 90. Okay, so here's our little list for inverse sine. The domain is from -1 to 1. The range is from -π/2 to +π/2, or if you're in degrees, that's -90 to 90. Okay, that's a big deal. That is like the end result of all of this criteria. So here's what I need you to know. I need you to know the criteria that we just said. We're trying to make a function. It needs to include 0 to 90, first quadrant. It needs to be continuous, and it needs to include all of the range of the original, or in other words, all of the domain of the inverse. Okay? Ultimately, for inverse sine, this is what we get, and this is always what it is for inverse sine. Every time, always. Okay? I'm going to do the same thing for cosine. I'm going to move very quickly for this part. Okay, again, cosine normally looks like this. Here's 2 pi. If I graph the inverse, it's going to look like this. Here's 2 pi. Again, all I'm doing is switching x and y values. Okay, now technically this keeps going, you know, even more. Okay, criteria. It needs to be a function. It needs to include 0 to 90. Well, this is 90. This is π/2 right here. So for sure I have to include that part. I want to include all of the range of the original, which means I need to go all the way from -1 to 1. And I would like it to be continuous. Okay, well, I don't want this because I don't want anything else on the right side of this graph. I do need to include the left side. Well, it looks like the left side that would connect up is this. So the rest of this is going away. Okay, so what did we end up with? Well, we ended up with from 0 to pi. Okay, so let's just double check our conditions. Is it a function? Does it pass the vertical line test? Yes. Does it include from 0 to 90 or 0 to π/2? Yes. Does it include all of the range from the original, which was from -1 to 1? Yes. Is it continuous or connected? Yes. Okay, so this is it. This is again for inverse cosine. Okay, so for y equals inverse cosine, the domain is -1 to 1. The range is, this is weird, 0 to pi, also known as 0 to 180. And that's it. Okay, it's always that for cosine. Maybe you want to memorize that. Maybe you want to do something with it. I don't know. And the graph looks like that little funky piece. Okay? And what's interesting to me, maybe not to you, is if I go into the calculator and actually graph inverse cosine of x. I'm going to do this on a Zoom 4 screen. Well, there it is. Let me go just a little bit higher so you understand where this thing really stops. Let's go up to 5. So there's that graph that's going from 0 to a little higher than 3, also known as 0 to a little higher than 3 is pi. Okay? All right, one more of these. We're not going to do them for the reciprocal functions. We're just going to do them for these, for the normal functions, tangent. Okay, so no, tangent's an ugly graph. Okay, remember at pi over 2 there's an asymptote. At 3 pi over 2 there's an asymptote. At negative pi over 2 there is an asymptote. Goes through 0, 0. Okay, and again, we're just working with basic, quick little sketches here to communicate what we're doing to make this into an inverse. Okay? All right. So if I'm trying to graph y equals inverse tangent, and I'm going to limit this so it's going to be a function. Okay, so first asymptote is at pi over 2. Next, there's one back here at negative pi over 2. This graph looks like this. And again, this is obviously not a function. And again, there are really a million of these. Okay. Well, for sure, I need to include the 0 to 90 stuff. Okay, 0 to pi over 2. Okay, so that means this chunk is gone. Okay, and any chunks that would have been down here, they're gone. Okay, I would like it to include all of the range. Well, the range for the original is all real numbers. So the domain of this needs to be all real numbers. So I need to go all the way from the left side of the graph to the right side of the graph. It all has to be there. Okay. Well, I still want it to be a function, and I want it to be continuous. So to me, the most obvious thing to do is to pick this other piece, and that little guy is gone. Okay, and that's it. So the domain for inverse tangent is all real numbers. The range is going to be from negative pi over 2 to positive pi over 2, like it was for sine. The only catch is these are not included, so we don't use brackets. We use parentheses. Okay, and again, you could list that from negative 90 to 90 if we were in degrees. All right, so that's all of it. The question is, so what? What do we do with this? Okay, and so we'll do just a couple quick examples, and the rest we'll just have to deal with in class. Okay, so speedy examples. What if I have, let's say we were doing the sine of pi over 4, and now I want to do the inverse sine of that. Okay, let's talk about what's really happening, and then let's talk about what we can kind of get away with. Well, the sine of pi over 4, if you think about the unit circle, is square root of 2 over 2. So that is the value for this. So now if I do inverse sine, it's saying what was the angle? So undo the sine. Well, shockingly enough, it's pi over 4. So basically what's happening is these two guys are kind of canceling out. Now I say that saying, see, isn't that easy? Easy schmeezy, that's, yeah, well, let's look again. What if I was going to do the inverse sine of the sine of 3 pi over 4? With the logic we just did, it looks like they should just cancel each other out. Well, kinda. Here's the problem. If I just cancel those out, I would be saying it's 3 pi over 4. Okay, in other words, 135 degrees. But let me remind you of something we talked about just a minute ago. That's right here, that inverse sine is only supposed to have values between negative pi over 2 and pi over 2, or negative 90 to 90. And obviously those values do not include 135. So in the immortal words of Mr. Sanford, that ain't it. This is very, very similar to the last problem though. So the inverse sine of what? Well, the sine of 3 pi over 4 is still square root of 2 over 2. Again, thinking about unit circle. So inverse sine of square root of 2 over 2 is actually 45 degrees, or pi over 4. The problem is this. You have multiple ways to get that square root of 2 over 2. Inverse only deals with one of those ways. Inverse always has a single answer, not multiple answers. When we finished section 4.4, and we were solving trig equations, we had multiple answers possible in different quadrants. And then the problem was, you know, which answers do you want? Which quadrants do you want? Well, in this one, it's very specific. Inverse sine only ever deals with to positive 90 or to negative 90 only. So if there's something over here, you have to make it work based on reference angles. So a lot of what we're going to be focusing on are the reference angles. All right, let's do another problem exactly like it, only not like it at all. All right, let's do the sine of the inverse sine of, let's do, no, let's not do that. Sorry. 2 pi over 3. Oh, sorry. I know this is frustrating you, and I apologize. Inverse sine of, let's do square root of 3 over 2. Okay. This is a little more straightforward, and because you don't have to worry about where is it, because the where is it is taken care of with this. Okay, so inverse sine only has answers between negative 90 and 90, or negative pi over 2 and pi over 2. Okay. So what value, what angle gets you a sine that is square root of 3 over 2? Well, that's actually a 60-degree angle. Okay, so all of this becomes just square root of 3, I'm sorry, pi over 3, or 60 degrees. If I take the sine of 63 degrees, I'm back to square root of 3 over 2. In effect, they are canceling each other out, and since your answer is already going to be between negative 1 and 1, this is kind of taking care of itself. What if we do something that's totally different? So like, let's do the cosine of the inverse sine of square root of 3 over 2. Then we'll do one more problem after this, okay, and it's going to be a little different than that. Okay, so inverse sine of square root of 3 over 2, we just said was pi over 3. Cosine of pi over 3 is actually 1/2. Okay, and again, you can go back to the unit circle and kind of build, you know, all of the ordered pairs and stuff, and I don't want to take the time to do that, but you can work with that. Okay, okay, one more, and this is going to be a little different. What if we're doing the cosine of the inverse tangent of 3/4? 3/4 is not one of our multiples of 60. It is not one of our standard angles on the unit circle or anything like that. So for this one, really you need to think about a triangle, like just draw a triangle. Okay, so tangent is positive. What this means is the tangent of some angle is 3/4. Tangent's positive in the first and third quadrants, and it is y over x. So here's 3, here's 4. It could have been negative 3, negative 4. Okay? But remember, inverse tangent is really only between negative 90 and positive 90. So this guy is actually completely out of the running. So now what we're going to do is figure out cosine for this, and in order to do that, I need a hypotenuse. So this feels more like back in the first half of chapter 4, way back when we're doing like opposite over adjacent and all that kind of stuff. And in this case, adjacent over hypotenuse. So we need to know the hypotenuse. 3 squared plus 4 squared equals r squared. So this is 25. Okay, so cosine is adjacent over hypotenuse, and we're there. Okay. All right. The big thing to watch for is quadrants. Okay. What quadrants are we working in? And with inverses, they are limited. All right. Well, that's all my time in an extra 5 minutes. So, SanfordFlipMath, we are done.